Okay, so the first thing I want to talk about is what causes oscillations, and this is going to be an equation-free talk. Okay, I hope that's okay. I know this is a math talk, but I'm not going to give you any equations. All right. So what is it that causes oscillations? Well, there's two things that are involved in oscillations: positive feedback and delayed negative feedback. It's really important to have delayed negative feedback. So I'll give you an example, the well-known shower oscillator. All right? If you've ever been in a really crappy old house or something that doesn't have a really good shower, then you've probably undergone the shower oscillation. All right? So what happens is that you turn the shower on and it's really cold. So you turn the hot water up. And it takes a while. You keep turning it up and then it gets hot. And then you turn it down, and because it's a really lousy shower, it takes a while before it happens. And then it turns, then it gets cold again and too hot and cold, and you can do that forever, okay? So that's an example of delayed negative feedback. You're turning it up because you want it to be warmer, okay? And it doesn't get warm for a long delay, all right? So you can do all kinds of examples of this that are really not just a shower. When I first moved to Pittsburgh, I had this big old Moluccan cockatoo that I kept in her own room, and because it was an old house, it didn't have much heating in it, so I had this little electric fan in there, a thermostatically controlled fan, and I used to listen to that thing come on and off, and I sat down there with a stopwatch. And you know, it was very regular oscillation, and it was exactly this. There's this delayed negative feedback. Here, in this case, it really wasn't so much delay. It was more something called hysteresis, where it would come on at a certain temperature and go off at another temperature. But anyway, it's the same idea. There's this delayed negative feedback. All right. So basically, this is an example of a so-called dynamic instability. If the shower reacted instantly, you would get the temperature in one shot, but it doesn't. So you alter back and forth, but you still don't converge. And if this delay gets too large, you won't ever converge. Okay, you can eventually converge if it's not too bad. And essentially, the set point is not stable. Instead, there's an oscillation. For those of you who are math guys, probably have seen this sort of thing before. It's a classic example of this is something called the Hopf bifurcation, where you get an equilibrium point to a system of differential equations that becomes unstable as you change some parameter, and the way it becomes unstable is through imaginary eigenvalues crossing the axis, and you start to get oscillations. So that's sort of a classic example. Now fireflies, each one is a tiny oscillator. All right, the mechanism of the oscillation is not really known. All right, but they do. And I'm going to show you a little movie here. See if I can find. Oops. Let me find the movie here. Here we go. This is Trials of Life, I think. I'm going to show you just. I figured Mike had a movie, I better have a movie. I don't know if anybody can hear this. When the sun goes down, it's a British guy, so you can't expect to understand. Okay, but and it's really hard to see here. But I'm not going to mess with the lights because otherwise, I don't know. Oh, I want to get to the cut to the chase here. There we go. So after about 45 minutes after dawn, every insect is flashing synchronously. It's an amazing show. Okay, and let me show you another version of synchrony that's not fireflies, but it's really just as cool. And this is really something you can do at home, too, all right? But it's the same principle, and I'm going to talk about fireflies in just a second. But I want to show you this. This is 5 metronomes, okay, on a piece of wood, and there's a couple of Coke cans. And now, it's going to lift them up. And lay it on there. And this is really amazing. They have one of these, I've tried to make them, they don't work very well in my hands, as I said. But I have discovered the best, I tried it on Coke cans, and Coke cans are pretty, they're dented. And so the best thing is to tie 2 fishing lines from the ceiling and then attach it to there, and then it works really well. Okay? So you can, I've had students do models of this. It's very simple. And in fact, Huygens was the first person to discover this. He noted that clocks sitting on the same wall would synchronize. Okay? So what happens with fireflies is that they flash, and when they see another firefly flash, they alter the timing of their flash, but in a timing specific way, all right? And they only see a few fireflies around them in some neighborhood, and they're affected therefore by others. Is this enough to cause synchrony? So this is an example of what we really are interested in mathematically, is we have these little tiny microscopic rules, and from this can we get this big macroscopic pattern. All right, so in this particular case, is this enough to synchronize the insects? And to understand this, you have to think about, what does the stimulus do, okay? So what happens to the firefly when he's oscillating, when his light is going on, and he gets stimulated? So to give you I'm going to give you 2 examples that you might be really much more familiar with. One of them is deep inside your brain, every one of you, you have something called the suprachiasmatic nucleus, okay? This is a nucleus that generates 24-hour rhythms and controls what's called your circadian pacemaker. Everybody has this. Every living thing on Earth has a some sort of circadian clock in it, except for things really in the deep ocean, okay? Because the sun is always there, okay? It's a 24-hour rhythm. And any of you who have ever gone east or west know that it takes a while to adjust. And what's going on there is the light is coming into your visual system, and your visual system goes to your cortex, but it also sends another little line to the suprachiasmatic nucleus, and it attempts to entrain your circadian pacemaker by light. Okay, so what's going on when you go to California is the light is shifted relative to your face, but you eventually get phase shifted to it. Another example, and this is apocryphal, there was a guy in McGill that was attempting in the early part of the 20th century. Okay, I always like to say the turn of the century, and now I can't say that anymore. The turn of last century. Okay, the century when I was born, unlike most of you guys. Oh no, that's not true, is it? No. Okay. All right. So anyway, he was doing experiments on phase resetting of the cardiac rhythm. Okay, and the apocryphal story is that unfortunately he set it to a particular point which had a stable fixed point. And he didn't know enough math to kick it back. Okay, so he died because he didn't know math. So that's an object lesson. All right, so let me explain. The key thing to understanding oscillations is that the time that a stimulus comes relative to your phase in your oscillation, and like Mike talked about, I'm going to put everything in a circle here, all right? But instead of being in integer numbers, I'm going to have a continuum, say 0 to 1, or usually we think of 0 to 2 pi, okay? And so the stimulus comes along, and the red lines are the intrinsic timing, say at the flash of the firefly. And the stimulus comes along, and And if it comes along at some cycles, some points in time, it might make you flash earlier or it might make you flash later. So it can either speed you up or slow you down. So here's an example. I've taken the circle right here, the dashed line, and this is the time at which you flash. And then what the stimulus does is it shifts this circle over, okay? So if you plot the time difference from here to here on a nice graph, you'll get a picture that looks like this. So if the stimulus comes right after you fire, it's going to slow you down. And if it comes right before you're going to fire, it's going to speed you up. So right away, you can see immediately that this is going to encourage you to synchronize with the stimulus. Because if the stimulus is too fast, so it's here, or if the stimulus is too slow, in other words, the stimulus comes on after you flash, okay? So the stimulus is too slow, it's going to slow you down. And if it comes on before you flash, right before you flash, it's too fast, it's going to speed you up. So you can see that that encourages synchrony. If you flip these two around, then that will encourage you to go 180 degrees out of phase, okay? And so going back to the finger tapping thing, you've got two guys. Each guy is a stimulus and a responder, okay? And as you change the frequency, you change the properties of the internal properties of the oscillator in such a way that you destabilize the state which wants to go out of phase. So what happens is this enough to make the fireflies. So what I did, so a very simple simulation, you should take n insects and you place them on a square grid. Each oscillates with a natural frequency. And if we're close enough, one affects the other. Okay? So the stimulus after the flash slows you down, and the stimulus before you hit the flash speeds you up. Now, I'm going to try this. I don't know if it'll work. I think I have. There we go. All right, so you can see they're all out of phase, and now it looks like they instantly went into synchrony. What I did was I got bored with waiting, so I cut out a good chunk of this, because it does take them a while. It takes them a couple hundred flashes, but you can see they start out all irregularly, and then after a certain amount of time, at the end, they're flashing perfectly synchronously. So the point is that this is these simple local rules are enough to guarantee synchrony.